Hi, my name is Glenn Brisebois. I am an applications engineer here at Linear Technology in the signal conditioning group. I support op-amps, comparators, references, RMS to DC converters, and all the other interesting products here. Today I'd like to talk to you about how to drive difficult loads quickly, difficult loads specifically being capacitors. Using, for example, one of our good CFAs, current feedback op-amps, is an LT1397. I hate generalities, so let's do a specific problem. Suppose you have a variable load that's as high as 10 nanofarads, and you need to drive that load 1 volt in 10 nanoseconds. If you do the calculation, the I equals CV over T reveals that you need 1 amp to make this happen, and the amp has to stop and start within a 10 nanosecond window. Anyone familiar with amps and nanoseconds knows that they don't usually go hand in hand. An amp is a current, and any parasitic inductance in the neighborhood will spread that amp out and cause it to be difficult to start and stop. You might be just tempted to just find the right op-amp, say an LT1206 or an LT1210. The thing is that an op-amp that can deliver 1 amp, like an LT1210, will have large internal devices, and that means high internal capacitance, and that means not so fast. Also, a single op-amp with a single output has a single bond wire internally, and that means inductance. Now, don't get me wrong, the LT1206 and LT1210 are among my favorite op-amps. If you can meet your speed needs and current needs with a single 250 milliamp or 1 amp op-amp like the 1206 or the 1210, that's fine. What I'm showing you now is what to do when the single op-amp approach just won't do it. Another problem with trying to do this with a single op-amp is the transmission line, and that's where a lot of engineers fall down. They haven't understood transmission lines well enough to be able to tackle the problems associated with a high current and high speed. Signals propagate down the transmission line as a finite speed voltage and current change. The ratio of the voltage and current as it propagates down the line isn't just whatever you hope for. It's the characteristic impedance of the transmission line, the Z0. You're probably familiar with 50 ohm and 75 ohm cables. If you put a 1 volt step onto a 50 volt cable, say it arrives here, so it propagates down as a 1 volt 20 milliamp signal. When it arrives here at the load, if the load isn't 50 ohms as well, the load says, hang on, I need more current if it's heavier than 50 ohms. And that causes a reflection back down the line, basically a request for more current. But the requirement of fast means that you don't have time for reflections back and forth to get the right answer at the load. To make a long story short, if you want to get 1 volt at 1 amp to your load fast, you don't do it with a 50 ohm transmission line. Here we see an example of a parallel implementation of several fast op-amps. In my design, I arranged the op-amp in linear progression with the input propagating left to right and optional snubber termination at the end, and the output also propagating left to right with the op-amp outputs decoupled from the output trace with small 8 ohm resistors. In this case, what's critical here is the design of the output transmission line. Before I show you the layout, I want to basically discuss how to achieve low Z0 with the correct geometries on transmission line design. In this case, for example, for a 1 volt 1 amp step in 10 nanoseconds onto 10 nanofarads, that means a Z0 well below 1 ohm. To get very low Z0 in a transmission line, it means that you have to use a wide conductor and a thin dielectric. Consulting this wide-range chart of transmission line geometries, you want a very high width-to-height ratio, which is plotted along this axis. So here you have ohms, and here you have width-to-height ratio. Now, for low ohms, you want to be down in this region here. You can see that the width-to-height ratio here is 100. In this design that I'm going to show you, in fact, the width-to-height ratio that I achieved was about 500 using techniques involving Kapton tape and copper tape. So here's the layout I came up with. In this case, it's a quad op-amp. The outputs of the op-amps are at the corners of the quad package. The inputs are near the supply pins in the middle. The input here is propagating left to right, and at the same time the output is propagating left to right. But here's what's critical. Notice this blue here is the output trace. Notice how it's getting thicker and thicker as you propagate left to right, wider and wider, I should say. What that's doing is decreasing the transmission line and characteristic impedance fairly drastically. This initial trace here is about 50 mil wide. The output trace, by the time it gets to this end, is a full 2 inches wide. That makes for a very low impedance transmission line. Now, to achieve a high quality low Z0, in this case I only had a 2-layer board. What I did was put a layer of Kapton tape, 4 mil thick, over this as a dielectric isolator, and then on the bottom of that I put a layer of copper tape soldered down, just leaving the end here exposed for the final connection to the load. If you think about it, do a quick calculation, the 2-inch wide trace on a 4 mil thick Kapton layer, referring back to that chart of characteristic impedance earlier, the geometries, that works out to a width to height ratio of 500, which was actually off of that chart. Here's a picture of the results I achieved with this board. This is the input trace on the top. Not bad, it's got a 5 nanosecond rise time or so. Here's the output trace onto the 10 nanofarad cap. You can see the width of the rise time here is about half a division. I apologize for the poor graticule. That's a 10 nanosecond full rise time onto 10 nanofarads at 1 volt, and that's 1 amp. So basically during this period, an amp is flowing. In this period there's no current, in this period there's very little current. But that's starting and stopping an amp with fairly good edges within a 10 nanosecond window. If you have any questions, please feel free to contact me here at Linear Technology. You can go to our website at www.linear.com. We have a lot of fine products. We have faster op amps, slower op amps, micropower op amps. Thank you.